also to introduce this notion of deformation. And in physics, there is two basic concepts. That maybe I can start with the relationships. And two fundamental concepts in physics. The state, the concept of state, and the concept of observable. And now let us see what is the correspondence, what is how they are handled in the classical mechanics. And in quantum mechanics. And what is the state here? Then the state for classical mechanics are just points in a manifold M. And for quantum mechanics, this is a projective space. It's Hilbert projective space, that's it, Hilbert. That's denoted by P and H. And what are observables here? And observables for classical mechanics are functions in space of quantum, in the space of functions over the variety of the manifold M. And this space has a structure of commutative algebra. Associative commutative algebra. And an observable for quantum mechanics is a self-joint operator. And we use mainly bounded operators. And now what is the value of an observable? This is just the value of f on a point M of the variety. And for quantum mechanics, this is a spectral value. Spectral value of an operator H. And we are also interested in the dynamics. And this is here for classical mechanics, it's ruled by Hamilton's equation. And of course, for quantum mechanics, this is Schrödinger equation. This is the dynamics of states, and now the dynamics. And the dynamics of observables. And this is the equation is the following: df of dt is fh, looks like u will, and here H. AGT, and this is the bracket AH. And maybe the last observation, and the most interesting one, is the structure of algebra of observable then here we have an algebra A. The vector space is the set of function. Function here I mean functions from M to R or C. And we have a pointwise multiplication, and we have also a bracket. And this is what we call, this triple defines what we call a Poisson bracket, Poisson algebra. Then, of course, this algebra is commutative, because the pointwise multiplication is commutative here. And for quantum mechanics, what we get here is A over these bounded operators, and this algebra is non-commutative and associative. And we have these two types of this algebra. And now showing this table, in fact, to show that in physics appear some algebraic structures. And here this algebraic structure involves this associative algebra and involves also a bracket. And this triple will give Poisson algebra. I will define what Poisson algebra later. And in quantum mechanics, we have this non-commutative algebra, and some people think because we are always looking for a connection between quantum mechanics and classical mechanics, and some people think that we can get a quantum mechanic as a deformation of classical mechanics, in the sense that we usually talk about quantization, and by quantization we mean a deformation. And here, starting from Poisson algebra, we deform this commutative multiplication in a non-commutative multiplication, and this non-commutative multiplication is called usually a star product, and it defines a non-commutative associative algebra, which is a quantization of the Poisson algebra. And this is this is related to deformation theory, as I will show later. Okay. And here you can see that we need to handle this associative algebra, and of course we have plenty of algebraic structure which are interesting. And let me just now give you an overview of algebraic structures. And in fact, usually what we need. Overview, let's write overview of algebraic structures. That what one need is first a K-vector space. If we don't want to work with models, then here K is a field. If you want algebraic closed field, K vector space, and we need a multiplication. And a multiplication is just an operation. And we need an operation or multiplication or product. We can use whatever we want. And we usually need a binary operation. But we can also use n-ary operations. But a binary operation, what is it? It's just let's call it mu. Huh? That's just is a bilinear map from A times A to A and to x, y. We associate mu x, y, and this is a bilinear map. But in general, we can use also n-ary operations. An n-ary operation is let's call it m, and this is from A times A times A to A, then to x1, x2, xn. We associate m of x1, x2, xn, and this is n-linear. And what is skew symmetry here? Sometimes we assume that the operation is skew symmetric. We say that M is skew symmetric. If skew symmetry means that M of, in general, for sigma belonging to the permutation which is a permutation Sn, we should have M of x sigma 1 x sigma n. This is equal to minus 1 sigma of m x1 xn. Okay. Then for example, for binary, we need to use S2, and we have m of x1. Then we have only one transposition, x2, x1. For example, this is minus m of x1, x2. Okay. And we say that it's, what about symmetry or commutativity? Then you know what is commutativity, of course, for binary, but for n-ary, this means that the sum over all elements of Sn of minus 1 to power signature. Oh, this is signature of sigma, of course. Signature of sigma of x. M of x sigma 1 x sigma n, and this should be 0. Now what happened for binary? For n equal 2, then we have only the sum here, we have only the identity or the transposition. Then we get m of x1 x2 minus m of x2, x1, this is 0. Okay? And you go over what you do. Now, what kind of algebra we can have? Of course, this is usually where we assume also some axioms. And in this world of what we call non-associative algebra, we also include associative algebra. Then the first structure we have seen here, which is very important, is this associative algebra. And to get associative algebra, we need an operation. Now we are using n equal 2, but of course we can talk about the associative algebra for n different from 2. But then what we need, moreover, the axiom that's saying that for any x and y, the multiplication is mu. It's mu of x. Then for associative, let me introduce this the associator. The associator is a trilinear map which applies to 3 elements, x1, x2, x3, and this is mu of x1, x2, x3 minus mu of x1, mu of x2, x3. And this associator should be 0 for associative algebra. This is exactly what you know. And what we have also is Lie algebra, and this is also important structure, algebraic structure. And to get the algebra, it's also give you the definition for n equal 2. Maybe you know it already. And this is binary operation, and we need skew symmetry, and also Jacobi condition. And we express Jacobi condition in this way. If you have x1 bracket of x1, x2, x3, and you consider cyclic permutation, and this should be 0. Okay? This is the two main operations, and there is a connection between them. Now let us consider, of course, we can talk about morphisms. And an algebra morphism is if you have A with a multiplication mu1 and B with a multiplication mu2, and we can assume that it's Lie algebra or associative algebra, whatever you want. Then the morphism here is a map phi such that you have phi of mu1 of x, y. This should be mu1 of mu2, sorry, of phi of x, phi of y. Okay, and we have. Then we can talk about categories, and there is a connection between the category of associative algebra and the category of Lie algebra. And then there is a functor here, let's call it Lie. And if you take an associative algebra defined by the vector space A and the multiplication U, then you can associate a Lie algebra where the bracket here, where the bracket of x, y is the commutator. let's write it like this, mu of xy minus mu of yx. Okay? Then this satisfies this is skew-symmetric and also satisfies the Jacobi condition. And there is also a joint functor u and to any Lie algebra we can associate an associative algebra, which is if now we have G with the bracket, which is Lie, then we can define UG to be the tensor algebra TG, then which is multiplicative here, which is associative. We have multiplication which is associative here, and we take the quotient with an ideal I, and I here is generated by x tensor y minus y tensor x minus bracket xy. Okay. And this relationship is interesting. Then, if you are interested in G models, then this corresponds to UG models. Okay. And now the question is, what kind of algebra we can get if we, instead of taking the commutator like this, we consider the plus algebra. And this is also an interesting algebraic structure. Now, and this is called Jordan algebra. And Jordan algebra is defined by the following axiom, that the associator of x squared y x, this is 0, and very often we assume that also that it's also commutative. And from an associative algebra, now if A mu is associative, then you can correspond an algebra A with a multiplication that's called dot, and where x y is defined by mu x y plus mu yx. Okay. Then this is maybe, and physicists, of course, use very often this Lie algebra or associative algebra, but some physicists also think that this Jordan algebra may play a very important role, and especially the exceptional algebra, because all Jordan algebra cannot be given by an associative algebra, and there is some exceptional one, and one of them seems to be very important for physicists. And of course, we can get other type of algebraic structure. We can, for example.
So every Jordan algebra is commutative.
Sorry. Every
Jordan algebra is commutative.
Yes. Yes, this is the definition.
Even exceptional ones also.
Of course, yes. Yeah. Then we can also address the question: what kind of algebra gives you a Lie algebra? Of course, if you by using commutator, then of course this associative algebra. But are there other type of algebra that gives Lie algebra by commutator? Of course, there is. And this type of algebra is called Lie admissible algebra. And it could be classified also. Algebra. then the readmissible algebra is A nu such that A with the commutator is an E algebra. And these algebra could be classified using subgroups of S3. If you take G, let G be a subgroup of S3, then you can define it's a sum. Is it the sigma belonging to G of mu x now if your algebra multiplication satisfies the associator of x sigma 1, x sigma 2, x sigma 3 equals 0, and of course here we have A with mu. A here is just a vector space, and mu is an operation. And if this mu satisfies the associator as defined somewhere here, where is the associator? Yeah, here. If your mu, if the associator is this quantity, if the associator satisfies this equal to 0, then A mu is readmissible. Okay. And of course, if you take G to be the identity, what you get it's exactly the associative algebra. This is just the associator. The associator equal to 0. Then this is associative algebra. And now let's, for example, take G is the identity and transposition 1, 2. And what you get here is the associator of x1, x2, x3 minus the associator of x2, x1, x3 equals 0. And this class of algebra is called pre-Lie. And it's also very important. And this is this defines what is called pre-Lie algebra. And of course, this is left pre-Lie algebra. And of course, you can define right pre-Lie algebra by taking the transposition 2, 3. And you can also take other subgroups of S3 and get readmissible algebra. But people are mainly interested in this pre-Lie algebra. It works for any subgroup of S3.
So identity is being assumed, multiplicative identity is being assumed?
Sorry?
Unit element is being assumed in the algebra?
For the moment I don't assume that associative algebra is unit.
Okay.
But we can add it as a...
So we don't need, for the readmissible, we don't need the unit element?
We don't have, as for the algebra. Okay. Then only one word maybe about Enery, because I mentioned Enery operation. But for Enery,
So why is there a minus before associated to x to x1 x3?
oh no.
associated X.
Oh, because I made a mistake here. It's -1 to the signature of sigma. Thank you. And now, just one word about ternary operations. And these operations also have interest in physics, and they came from physics. And maybe you know, as I mentioned before, the Hamiltonians. And usually, to build some physics, you need a Hamiltonian. Okay. And the idea of Nambu, who got a Nobel Prize, is to use more than one Hamiltonian. And what about physics with, for example, two Hamiltonians? And if you want to use two Hamiltonians, what you need is a bracket with 3 legs, and a ternary operation. Then we need a ternary operation, and it turns out that when you do what is called Nambu's mechanics, then two Hamiltonians. What we need is a ternary bracket. A ternary bracket, and what will be the Jacobi condition? The Jacobi condition here, the Jacobi condition that I mentioned here is you can view it also that as the adjoint action is a derivation, and you can do the same here and assume that the adjoint, when we define it, usually what we define the adjoint is a map. For example, here we should fix 2 elements, x1 and x2, and the adjoint is a map going from A to A to an element y. We associate, since you have a ternary bracket, x1, x2, y. This is left action. And with Lie algebra, we have only one element here, and we act by bracket x1 y. Okay? And the Jacobi condition is exactly exactly means that this action is a derivation with respect to your bracket. And here we also to generalize this Jacobi condition for ternary operations, we have to say that this joint action is a derivation, but for the ternary operation, and it could be we can write it as follows. Then let me write it directly by brackets. Maybe it's better. Then x1, x2. We act on y1, y2, y3. Bracket on y1, y2, y3, and this should be should equal to bracket of x1, x2, y1 plus y2, y3 plus y1, x1, x2, y2, y3 plus y1, y2, x1, x1, x2, y3. This is what we call Nambu identity. And in fact, Nambu didn't find this identity. It was discovered by Filippo, mathematician from Novosibirsk, and sometimes it's called Filippo identity. in fact, Nambu discussed the mechanics, but didn't give the algebraic interpretation. And the algebraic interpretation of this Nambu mechanics was given by Takhtajan from St. Petersburg School. This is the point. And also, from the algebraic point of view, it was discussed by Filipov, who gave the properties of this kind of algebra. Of course, not at time, but we can also discuss associative general. We can also generalize associative algebra for ternary operations, and here this is one of the point of view. We can also generalize this Lie algebra in different way. I mentioned here that we have just to take a permutation. The permutation of the three elements. We can do this also for ternary operations. Maybe let me mention this another generalization. It could be given by the following identity: the sum of x1 x. Okay, let's write it this way. x1, x sigma 1, x sigma 2, or maybe x2, x3, x4, x5, like this. And I can use this symbol, which means that, and I do the cyclic permutation. I take the cyclic permutation of these 5 elements: x1, x2, x3, x4, x5, and this is equal to 0. This is another possibility for generalizing the algebra, because this Jacobi condition, you can view it as in this way, that a joint is derivation, but you can also view it as a cyclic summation, say a sum of cyclic permutations of the elements involved here. Okay. And for associative algebra, there is also different point of view. For us, you can just move the brackets and take also 5 elements, but you can also take a summation. Then you got what is called partially associative, and this is what is called totally associative ternary operation. And this type of algebraic structure was developed also for some operads interest. And Laudet was interested to discover some new operads and try to handle this type of algebra.
In Jacobi identity, we are dealing with 3 variables, and here we are doing each 5 variables.
Yeah, because we are dealing with the ternary bracket. Because here the bracket is the bracket here is the bracket is a map going from A times A times A into A. Then you need 3 elements: x1, x2, x3. To get the bracket of x1, to get the bracket. This is the ternary operation.
So is there any possibility of having 4 variables? Like
no. Because if you take only 4, then you get, with three you get one element, and you need one more. Huh?
Yeah.
Okay. But if you have only 4, then you get to this. And then your operation becomes binary. Okay. Okay. Let me stop with this. And we can also dualize things. And to get what in this quantization stuff. Maybe you heard about quantum groups, and what quantum group is. The quantum group is also related to some algebraic structure. Let me mention this quickly. and it needs and quantum groups also are sort of deformation of usual groups, but they use so-called Hop algebra, which can be obtained by dualizing these operations. Of course, here I use the product, but you can put all this linearity in the tensor product, and to get associative algebra, as it was done yesterday by Anita, you can just take linear operation from A tensor A into A, and your the associativity condition could be written with the diagram, and we start with three elements, and you apply new tensor the identity here and get two elements, to A tensor 2, and of course you can do it by using the identity first and then the multiplication, and here you use the multiplication and get to A, and same here, and here you get to A tensor A, and by using the multiplication you would like to get to the same element. And this diagram means that the multiplication is associative. And now we have linear map. You can dualize. And now we get to dualize things. Then by dualization we get some map. Then if you write it like this, and then we go from the dual of A into the dual of course. Here, the dual should be the dual of A tensor A. Let us assume that A is finite dimensional, and this assume that this is the same as the dual of A tensor A, tensor the dual of A. Then you get an operation from then this delta. This delta is a map going from B to B tensor B. Okay? And now we would like to get what will be the equivalent, the corresponding of the associativity for such an operation. And to get this is very easy. You have to just reverse the arrows here. And then you reverse the arrows here and get to. And here you use you replace U by delta, and here delta tensor the identity, and here identity tensor delta, and here is delta. And then this delta is co-associative, and we use the word co now. Co-associative if we have the following condition holds. Delta, if delta tensor the identity composed with delta is equal to identity tensor delta composed with delta. This is what co-associativity means. And now in fact the idea to use this type of algebra comes from physics. Do you know what is the main property of groups? The main property of groups are the auto duality. If you take a group and you dualize, you get a group. But if you take an algebra and you realize you do not get you do not get an algebra. But now we try to get something resembling to groups, and for this we need more complicated structure, and we need to include this co-multiplication, and then we define what is called bialgebra. And bialgebra is given by a vector space, a multiplication, and also a unit. I didn't talk about unit, but yesterday Anita mentioned that. And a co-multiplication delta and a co-unit epsilon, in which A mu eta is an associative algebra, and A with delta epsilon is co-associative algebra, and the co-unit. This is the definition of co-associativity and co-unit. Unit you can view it also as a map. In this language, Hopf algebra language, we need to handle maps, and the unit is just a map going from K to A. And of course, this should be linear, and since it's K-linear, this is generated by eta of 1. And this eta of 1 is usually what we denote by the units. Okay? And then the co-unit should be is a map going, co-unit epsilon is a map going from E to K. And it should satisfy the following. Identity tensor epsilon composed with delta should be the epsilon tensor, the identity, composed with delta, and should be the identity. This is the co-unitarity axioms. And of course, to get this bialgebra, you need also a compatibility condition. And this compatibility condition could be said as this delta and epsilon should be algebra map, which means that delta of x, y, this is delta of x, and this is the dot in the tensor product, delta of y, okay, and epsilon of xy is epsilon of x, epsilon of y, and we have also, it should be compatible with the unit, and epsilon of 1 should be 1, and epsilon of and delta of 1 should be 1 and so on. Okay, and this is the definition of bialgebra. And to get to Hopf, now if you have this, then you can construct a convolution product. And this convolution product is built on the algebra from the morphism of A on A, and it is defined as follows: if you take f and g belonging to n on A, and then you define this convolution products to be mu composed by f tensor g composed by with delta. And now, and A with this convolution product is unital associative algebra, and the unit here is eta composed with epsilon. Okay. And we call an antipode, which also plays a very important role. An antipode is a map S from A to A, such that S tensor the identity it's the inverse of the identity with respect to this convolution project. And this is the identity tensor S, and this is equal to eta composed with epsilon. And what Hopf algebra is now, and Hopf algebra is given by it's a bi-algebra. It's a bi-algebra with admitting an antipode. Admitting one C for antipode. Admitting an antipode. Then the main examples for this maybe KG. Now let's consider a group. In fact, it started with groups. That's why we have these quantum groups. Then if you have a group, then you can construct group algebra KG. This is a group, classical group, and the KG. And KG is an associative algebra, which is generated by elements of AG, where G is in G, and the multiplication here AG G dash. This is just AG G dash, and this is an associative algebra. It's an associative algebra, and the unit, of course, the unit is E1, E1 in the group, and you can undo this with Hopf algebra structure by considering that delta of EG is EG tensor EG. Okay. And then and S EG is EG inverse. Okay, and then you get the Hopf algebra structure.
What is the co-unit here?
And the co-unit is always 1. EG is always 1. Okay, and then this is a Hopf algebra. Then KG is a Hopf. Okay. Okay. Then and another example. This is let's say this is the first example. Now the second example is you consider G to be a Lie algebra, and you consider UG, the universal enveloping algebra of G, and this is an associative algebra. This is associative algebra. This is universal enveloping algebra. Okay, let's write it. Universal. Which is associative, and then you assume that delta of x for x, and here of course for universal enveloping algebra we have a very important theorem saying that the basis of this algebra is given by monomials. Monomials basis. It's called Poincaré-Birkhoff-Witt basis.
So this theorem is true for regardless whether G is finite dimensional or infinite dimensional?
Finite dimensional.
Okay, finite.
Yeah, finite. then let's consider that x1, xn, it's n-dimensional. Then the basis for this universal enveloping algebra is that the form is given by x1 alpha 1, xn alpha n. And these xi are generators of your Lie algebra. And for this, for an element of G, delta of x is 1 tensor x plus x tensor 1. Okay? We say that it's primitive. Okay? And of course here delta 1 is always 1 tensor 1. 1 tensor 1. And if you want to get the delta for other elements, then you have to use the compatibility condition. Here. Then if you want to, since it's if you want to have delta of x1, x2, then delta of x1, x2 is just delta of x1 times delta of x2.
So this times is the ordinary product in the...
This is the ordinary product for tensor product.
For tensor product.
Yeah?
So we are in the tensor algebra.
Yes.
Oh, we are in the tensor product algebra, and there we are taking the product.
Yeah, if you want, you can take the right. x1, delta of x1 is x1 tensor x1. Now, then usually here we use what is called Swindler notation. This delta of x is something like this: x1 tensor x2. And here, if you multiply this by something like y1 tensor y2, okay, and what you get is something like x1 here times y1 tensor x2 times y2. This is usual product in tensor. Okay. Let me finish with this. Okay, it's just to connect this to deformation theory. Okay. So here.
You have to wait another hour.
Let me just to conclude with the connection of this Hopf algebra to quantum groups and to deformation theory. And we are done with this first half. Yes. In fact, then we have for what we have is usually what we have is G. For simple Lie algebra, simple Lie algebra. For simple Lie algebra, you have this UG is also simple as in associative algebra. Okay. Then, if it's simple, we see here that we cannot deform it. There is no deformation. But if you consider that if as an associative, then no deformation. Then in fact, if we want to deform this universal enveloping algebra, what we could deform would be the co-multiplication. And then we have this UQG, which are called quantum groups. And this quantum groups, then here what we deform is roughly speaking, we can see that this is non-commutative and non-co-commutative deformation of UG. Okay, and what you get here is a quantum group. And then it's related to deformation. It's just quantum group is a deformation of usual nu G. And the idea for the idea from this St. Petersburg school, Fadeev and his collaborators, was to consider a group, and then if you have a group, then you consider the function on the group, which means the set of f going from G to R, for example, or C. And this is a commutative algebra. The commutative algebra, and we deform this to non-commutative algebra. And then the question is, what is the corresponding here? What is the group for this commutative algebra? We have the corresponding, which is the usual group. And now let's think what is the corresponding the group structure corresponding to this non-commutative algebra deformation, let's say. And this here, what we get here, what is exactly what we call a quantum group. It's the corresponding in the deformations. This is what we can call a quantum group. And the first example was given by this St. Petersburg school, mainly by Peter Kuish, who was the first, and he discussed this quantum group for SL2, which is the first simple Lie algebra, and got to this quantum group. And of course, all this was popularized by Greenfeld, and now this shows, gives you a picture of why we are interested in this Hopf algebra, why we are interested in these quantum groups, and also why deformation is important. And the aim of the next lecture is maybe to define what is a deformation. Now it's time. Thank you.
Are there any questions or comments?
Yes. So this quantum group always can be constructed?
Oh, no.
So in the case, or in the original example of SL2,
yes.
it can, so what was the original example? What was the, so deformation was deformation of SL2?
Yes.
And then
USL2.
USL2.
The enveloping algebra.
Yeah. So in that case, the quantum group can be constructed.
Yes. Yes. This was the first example of quantum groups.
And it's actually a group.
No, it's not a group, because it's a Hopf algebra.
So, I mean,
in fact, these quantum groups are not really group, but they replace the groups in this quantum space or this non-commutative space.
So if that is a Hopf algebra, how is the non-commutative deformation that you have below that arrow? How is that related? Because in the left side, you have the algebra.
You mean for this group?
No. So you said that how quantum groups arise is that we take some group and the algebra functions on it.
Yes.
And then we deform the algebra functions to some non-commutative algebra.
Yes.
And then there is some Hopf algebra corresponding to.
No. I'm sorry. This is a general picture, and what we get here is some non-commutative space.
Yes.
And now, if you want to relate this to, then here we have this space of function, and we have here non-commutative space of function, because this now what we get here is non-commutative. Yeah, here is function. It's not related to universal enveloping algebra here.
Maybe we should take a 5-minute break and then you can discuss during that, so at least people will have a minute
yes,
to
no problem.
read,
Yes,
and then we can continue, because we're running late.
Okay.
Okay, thank you.
Let us thank the speaker.
And I'm done with this algebraic structure. Let me come back to, this is, then we are dealing with algebraic structure. And Anita mentioned yesterday that homology plays an important role in in deformation theory. And let me recall, and she gave us the complex, the homology complex for associative algebra, the Harshad homology complex, with values in any a bimodal. But in fact, for deformation theory, what we need is in Anita's talk, we need to put m equals a, which is a bimodal. And let me recall you the differential and delta of then the cochance f, if f belongs to Cn AA, which means that this is the set of maps from A tensor n to A, and delta n of f applied to x1 xn plus 1, and according to what we have seen yesterday is f of a2, then this is the dot, which is the multiplication. And now A is an associative algebra. A is an associative algebra, and this is a Harshad complementary map. It's defined by f a2 an plus 1 plus the summation minus 1 to I of f a1 ai minus 1 times ai an plus 1 and plus or minus 1 to n of f a1 an times a n plus 1. And what we need is delta 1 of f applies to x1, x2, and this is a1, no, I'm sorry. I'm trying to fill my notes and I'm writing that a is x. Okay, let's change here. Okay, and a1, a2. Then this is a1 times f of a2 minus f of a1, a2, and plus f of a1, a2. And if you take this equals 0, then you get the derivation. And we need also delta 2 of f, of 5, let's take 5, of a1, a2, a3. And this is a1 f of a5. 5 of a2, a3. Minus 5 of a1, a2, a3 plus 5 of a1, a2, a3 minus 5 of a1, a2, a3. Okay, have this in mind. And yesterday Anita announced some operations related to this to this homology, but she didn't have time to do it. And there is a so-called Gerstenhaber bracket. Then the Harshad complex. Has a bracket, which is defined here. Then the bracket, we have this bracket going from Cn, Cn of, let's see, m here, AA times C of n AA and what we get here is a coterm with n plus n minus 1 of AA, and it's defined in this way. If you have phi and psi, and this is phi composed with this circle is not composition. Let's put subscript G for Gerstenhaber minus 1 to n minus 1 times n minus 1 of psi composed with phi. And let me define this where this phi composed with psi, and this applies to and this Gerstenhaber circle is defined in this way. A1 applied to A1 am plus n minus 1, and this is equal to sum of from I0 to m plus n minus 1 of minus 1 this is n, okay. I n minus 1 of phi of A1 AI, and then we apply psi to AI plus 1, sorry, to I plus n, and again here we have I n plus n plus 1 to I n plus n minus 1. And this is and it turns out that if you consider this C, this set of coterms with this circle, then it has a structure of 3D algebra. I defined what 3D algebra is before. Then this is a 3D algebra. And if you take, if you consider, maybe I can put here G as well. Yeah, for Gerstenhaber, this Gerstenhaber bracket with this Gerstenhaber bracket, and this is a graded the algebra. And this applies an important rule. There's some observations here. The first now, what happened if my let's say that the algebra is defined by the multiplication mu. Huh? What happened if if I take mu? Because mu is a bilinear map. It's a true quotient. Huh? Then what happens? This is 0, and this is if you write for bilinear map mu, the Gerstenhaber bracket mu, this is equal to twice the the mu composed in mu. It's ternary operation. Huh? Yes. Then the Gerstenhaber mu composed in mu, and this is exactly mu of mu. Okay. Mu. This is applied to x, y, z, huh? And this is mu of x. So of x, y, z, huh? Plus or minus. Plus is plus. Huh? Mu. Then it's twice. Huh? And mu composed in mu applied to x, y, z this is mu of mu of x, y, z minus mu of x, mu, y, z. Okay? Which is then if this is 0, and this is exactly the associativity condition. Okay? Then this is the associativity condition. Okay? Then if you want to check whether your operation, you take a binary operation, and you want to check whether this operation satisfies the associativity condition, then you can just you need to take this Gessenhaber. You consider mu the bracket of mu comma mu with this Gessenhaber bracket. If this is 0, this means that mu is associative. Then this means that this is equivalent to say that mu is associative. Associative operation. And this is one of the observations. And the second observation. Now what is now you fix as a first argument mu, and you keep this free. Huh? And this is exactly delta or maybe let's say phi here, phi belonging to C n of AA. Then this is delta n of phi. Then you can express the co-boundary operator using this Gessenhaber bracket. And next, when we want to check whether our deformation is associative, what we need, if this mu is replaced by mu t, some deformation operation, then we need to check that the bracket mu t is 0 using this. Yeah, and then we have this connection to homological algebra. Now let's start with definition of deformation theory. Oh, maybe maybe another word. Yeah. I can introduce the story, and then but what about deformation theory? Let me mention the first. There is, I can say, 3 points of view. The first point of view is the functorial point of view. Which says that a deformation is a functor, and def of G, which goes from the category of local Artinian K algebra, local Artinian K algebra with residual field K into the category of sets. And this approach was developed by Grothendieck. We celebrate a lot of things from Grothendieck this year, and let's say Schlesinger, maybe Lauder, Lucy, and many people. And this is very general, let's say, a general point of view. And the second point of view is to say that here we have we start with the K algebra. We start with K algebra and replace the field K by any commutative K algebra. Let's call it B. Okay.
So I mean, this second point is also a functorial point of view.
In fact, it was taken from this. It was inspired from this, but it's a particular situation.
So we take some K algebra and we.
Yeah, we fix some K algebra, and it becomes. And now I will show how and this is this commutative. This is what we can call the global deformation, and what we need is an augmentation. Epsilon from B to K is an augmentation. And a deformation is a multiplication on the tensor product B tensor A. Is a multiplication in the tensor product B tensor A.
So here was the original algebra.
A is the original algebra. Okay. Yes, I fix it. Okay, and such that this epsilon tensor the identity, which goes from A tensor A into B. Into A, which is K tensor A, which is isomorphic to A here, and this is an algebra.
So this is B tensor K actually. From
No, this is a. Oh. Yes. Yeah, here is B. It is an algebra homomorphism. Okay? Now this is a
You're saying that you start with an arbitrary K algebra equipped with an augmentation. The augmentation is given as part of the structure.
is a part of the deformation.
Oh, okay, I'm sorry.
The A is a K algebra.
Yeah.
And now we would like to deform this A algebra. And to build what we can call the global deformation, we need a commutative K algebra B, which will be the base of the deformation. And the deformation is a multiplication on B tensor A. Okay. Now, of course, we need B and we need also an augmentation. Then the deformation here is defined by a pair, where B by a pair B epsilon. B is a commutative K algebra, and epsilon is an augmentation only. Okay.
You don't ask any compatibility with mu of this operation. You have the mu on A tensor A to A.
Yeah. Then let's write the multiplication now. And this what we need is that this new multiplication. Let's call it mu B. This new multiplication should be associative. This is the connection with the. Then this mu B applies to A tensor, let's say X. B tensor Y. And this is A, B, tensor identity. You can write it like this. Of course, this is bilinear. This tensor is a bilinear tensor product. Then I could write it in this way. Then mu b of 1 tensor x, 1 tensor y. And this multiplication mu b should be associative, is associative. And this is then we have this multiplication, and with the co-unit, not the co-unit, with the augmentation applied to mu b, this is a compatibility condition also, 1 tensor x this should be, and this is your question period. And this should be 1, if you apply this should be 1 mu x tensor y. This is the connection to the original multiplication.
So the tensor product is over K for B and A tensor product is over
It's B, no, it's over B.
It's over B.
Yes, it's B linear.
That's some commutative algebra.
And this mu is B linear.
That tensor product is over K. But
Yeah, sorry. Here, this tensor product, you're right. This is over K, and this multiplication mu, and mu b is and the multiplication is a multiplication in the tensor, which is, that's complete definition, which is B linear. Is it clear now? And the B linearity is expressed here. Mu of A tensor x, B tensor y is defined like this.
okay, so you are considering B tensor as a B module.
Yes.
By embedding of B.
Yes.
inside B.
Yes.
Okay.
And let me say, give some names. This approach was used mainly by Fialowski, which has some joint work with Mukherjee. Sorry, if is it correct? M-U? K-H. Okay. G here?
It's not G, it's J.
G again.
One more.
Oh, yes. That, okay. And also Anita did some work with Fialowski. Then Fialowski was first interested in deforming weak algebra, which is infinite-dimensional Lie algebra. Then this approach was extended to other algebraic structure. Maybe I should also give another Indian name is Ashish Manda. From Kanpur.
Where does the motivation for this come from, for this global deformation?
Yeah, now what is the motivation for deformation? Maybe I can answer. What is the motivation for deformation? In fact, when we deform, the motivations in general for deformation is to construct new object, starting from a given object. They construct new objects in general, and also and understand better the object, and also provide some invariance. You can use it as an invariant. For example, if your algebra is rigid and it cannot be isomorphic to another algebra which is not rigid. Okay. Now this is the motivation in general. And also if you consider the algebraic variety of algebra for a given dimension, if you consider, for example, the as, which is the algebraic variety as n, algebraic variety of algebra of dimension n.
But how do we define this?
Now, to define this, what we have to identify, we identify the multiplication to its structure constants. Now, since I'm saying that the dimension of A is n, I can consider that E1, En is a basis of n. I can fix this, basis of A.
So A can be non-commutative also.
Sorry?
A can be non-commutative also. In this definition,
A,
can be non-commutative also.
but A is a k-vector space. Yeah, of course. You mean the multiplication. Yeah. A is vector space,
Yes.
and now your multiplication, of course, can be non-commutative. Yes. Yeah? For any associative algebra. I can even
So you
don't
can-
care about units.
You can apply this, for example, to Hamilton's quaternion.
To what?
To quaternion also you can apply this.
Yeah, but quaternion are examples of associative algebra.
So in this definition of the Sn, we are taking A to be an associative algebra.
Yes. But Sn is the set of all associative algebra of dimension n.
Okay.
Huh? And I can view this set
As a variety.
as an algebraic variety. I can show you.
Okay.
Huh? Then you fix your basis for the vector space, and now you say that, of course, according to the bilinearity, your multiplication, you just need to define it only on the basis.
So A comes equipped with this mu.
Of course. Yes. Now the element of this ASN is pairs of vector space and multiplication. Okay? I don't assume that there is unit. If you want to assume the unit, you can also. It becomes a subvariety. And then we have here the multiplication AIEG, and this is an element of A, and it could be written as a sum of CIG K, EK, and we sum over from 1 to n. Okay? And we call this set of CIG K with A, G, K running from 1 to n, the set of structure constants. Constants. And of course, this is the definition for any bilinear map, and all the bilinear maps are embedded in K. Then this bilinear map set is embedded in K to n power 3, a fine space.
Just by mapping to the structure.
Yeah, because if you give me a set of n power 3 constants, then it defines a bilinear map.
It's like n times n times n matrix.
Yes, exactly.
But that matrix need not be uniquely given. I mean, you can have another set of structure constants if you change the basis.
But for first, let's just say if you give me a set of structure constants, huh? and power 3 structure constant, it corresponds to binomial. You agree? Huh? Now, of course, this binomial should be associative. And now let's check what is the associativity condition. G K. Then I should check the associativity condition only on the elements of the basis. And if I do this, then it should write as mu of mu EI, EJ, EK should be equal to mu EI, mu EJ, EK equals 0. And they can now use this structure constant, and what we get here is the sum of C and G, K, let's say P, sum over P, and then from here I have EP, and it becomes C, P, K, Q, and sum over Q, EQ, and from this side we get C, G, K, P, and then C, P, C, P, no, C, I, P, Q, and this is EQ, EQ equals 0. And in fact, now what the algebraic variety, then here we have you can view this as variables, and you have n power 3 variables, and now you consider the set of polynomials with n to 3 variables, and here you have polynomials, and this associativity condition, you can write it as a set, as the algebraic variety associated to the ideals, which is given by the polynomials C, R, J, P, C, P, K, Q, minus C, J, K, P, C, I, P, Q. And this is for I, J, K, Q, running from 1 to n. We have this set of polynomials, and this is an algebraic, this is a quadratic algebraic variety embedded in the affine space k to n power 3.
Is it related to the Grassmannian in some way?
No, Grassmannian you assume some skew symmetry there. Okay. Then one of the question is, then you have an algebraic variety. Of course, what you could say is that 2 points in this algebraic variety could give you isomorphic algebra.
So there's no bijection between this Sn and the variety points. So there's no bijection.
With Sn?
So the set of Sn is not in bijection with the points on the variety.
What is Sn?
This
ASS and
so it's not a bijection.
with what?
I mean, so with the isomorphism classes of algebra.
Yeah, and to get the isomorphism classes, you need an action. Let me show you the action now. To identify 2 points which gives you the same algebra. You could have two points in this algebraic variety, which corresponds to isomorphic algebra. And this gives you a vibration of this algebraic variety. GLN acts on this ASSN in the following way. Then we have F, this is GLNK, yeah? F, and let's go identify, take just mu, the multiplication in this. Then if you take an element in GLNK and the multiplication in here, and you get F mu, which is a new multiplication here, and it's defined in this way. F where F mu of x, y, and this is just F inverse of mu fx, fy. Okay, then this is the action. Then we can say that two algebra are isomorphic. Two algebra mu1 and mu2 are isomorphic if there exists F in GLN such that mu2 is F mu1. Okay, and we can construct the orbit of mu, for example. And then this is the set. This is the set of all F mu, which is the same as F inverse composed with mu composed with F tensor F, and such that this F belongs to GLN K. Then you have the orbit of the fluoride. And since we are dealing with the algebraic variety, one question is how behave this the reducible component. Of course, you can always split your algebraic variety as union of a reducible component. Then the question about irreducible components of ASSN, then this question could be solved using deformation theory. And one maybe I can another result here since we are discussing this. And for example, if you okay, then we need some topology here, and of course the topology here is this Zariski topology, which is usually for with algebraic variety, algebraic geometry, and now the reducible components will be given in some case by the closure of the orbits. But it's now let's consider mu that if mu is rigid, I didn't define it, I'm sorry. Rigid means no deformation. If it has no deformation, in the sense I will show in a minute, then the closure of this mu is an irreducible component. Okay. Otherwise, then this is one of the observation. You can then if you add the number, then the number of rigid algebra could minorate the number of reducible components, for example. But if you want to organize your algebraic variety, to organize your algebraic variety with the reducible components, what we need the concepts of concept of degeneration, which is the dual concept of deformation. Maybe I will explain this later. And this sometimes is called specialization. Okay? Now this is, now maybe I can try to give a
This is
definition.
Zariski closure, basically.
Yes, yes, this is the Zariski. Yeah. Of course. Now that I mentioned here that we are discussing. Yeah? Okay? Now, we will not use this this approach, the second approach, but we will use a third approach. It was the approach given by Gerstenhaber, and in which this this B is a formal power series ring with one variables, and this is enough. And the third approach is formal, let's say one parameter formal deformation. In fact, here we use this B, which is the base, the base algebra for the deformation. It's just K, the formal power series ring T. It's commutative algebra, and you can, and of course.
So it's formal power series over which algebra?
Over what?
Formal power series over which algebra? The algebra we are trying to
Over K.
Over
K. Yes.
So
Yeah. In fact, the idea here is the idea here is just to consider the deforming is considered instead of K the formal power series ring KT. Okay? Now, which is the set of elements of the form sum of lambda K T to K 0 to infinity, where lambda K are in K. Okay? This is the main idea.
So does it have any augmentation also in this case?
We don't need here. Huh?
Okay.
We don't need here.
So
It's a local ring. Huh? The problem there is you have to take the kernel of this augmentation if it's not unique and okay. Then this is we have a local ring here, and you have only one maximal ideal, which is TKT. Okay. It's very convenient here, and we can work out. I don't know how much time.
5 minutes.
Only. Okay.
One should mention that here you're assuming now that K is a field.
Yeah, but K is the field on which is based our algebra from the beginning.
But I thought here we were assuming K was just some arbitrary commutative ring.
Here is still, K is still a field here.
Oh, okay.
But the algebra is based on this.
Okay, it's yeah. Okay.
Huh?
Yeah.
Our algebra is from the beginning is a K algebra. Huh? And this is the same field. And of course now we need to extend. We have our algebra A. A is a K vector space. Is a K vector space. And now we need to extend the coefficient domain from K to KT. And now we should define formal spaces. We need to define formal spaces AT which will be given by elements of the form sum of a k, t to k, k running from 0 to infinity, where a, k are elements in A. Okay? Then AT, this formal space, AT, is a KT model with the action then if you have sum of lambda I t to I, sum of x, let's say a, j, t to j, then this is in kt, this is in at, then this associate the element with double sum over I and j, or we can write it like this, p larger or equal to 0 and I plus j equal to p of lambda I x a j t to I plus t to p. Okay, and this is a trivial action. And now I want to make an observation, and then we can end with the definition.
So the action is term-wise, I think. Is it?
Sorry?
Action is term-wise.
Yes.
So the action is term. I mean.
Yeah. Of course. Then you have the summation here. You assume that is KT linear somehow. Huh?
So we are doing term by term multiplication. That's all, and we are just multiplying a.
Yes. And of course, the question is whether I can write this AT as KT tensor A, and this is not always possible. Huh? Then, in fact, what we have then if let f going from A tensor KT to AT. Consider this map defined as x tensor, let's call it lambda here, and this is lambda x, as I mentioned before. Then this map, then f is is injective. First observation that this f is injective. And the second observation that if f a is finite dimensional, if a is finite dimensional, then we have the isomorphism between a tensor kt and at.
So where is lambda is some power series over k,
Yes.
and x is some element of a.
Yeah. And this action is exactly what I mentioned.
So how do we define lambda x on the right hand side?
I think we should stop here.
Huh?
So I think time is over.
Yeah. So
Yeah, but let me just give the definition. Then I have used 2 hours to define something. It will be good job. And only just a few minutes. Then how to define now the formal deformation definition. Then let A be a K associative algebra, a K an associative K algebra. K algebra. Huh? Then a deformation. Let's denote by a mu 0 the multiplication with mu 0 with mu0 being the multiplication. A deformation of mu0 is given, is a KT algebra, AT mu t, where we will use the same idea as formal power series, and this mu t will be a formal power series. Where mu t equals to mu0 plus t mu1 plus t squared mu2, etc. And mu I are or mu k are bilinear maps from A tensor A to A. Bilinear maps. And this is now you can notice that if t equals 0, if the parameter t equals 0, then we get mu0. Where such is a KT algebra. That is, then I should assume that this, I'm saying that it's KT algebra, which means that this mu t is associative. That is, mu t is associative. Mu t is associative. We have mu t of, and since we have a KT linearity, then we can check the associativity only on elements of A. Then mu t of mu t, you can write it using this, okay, mu t of x, y, z equals, or minus mu t of x, mu t of y, z equals 0 for any x, y, z in A. I don't need to check the associativity condition for any elements in A t. It's enough according to the KT linearity to check it only in elements of A. And this is what we call deformation equation. And this is the deformation equation. And then the next work would be to solve this deformation equation. I will do it more.
Again, it suffices to do it on the basis elements.
Yes. Yeah, it's also enough to do it on the basis elements. And of course, the question is how to characterize this mu1, mu2, etc. when we get equivalent deformation, etc. I will discuss all these problems and solve this deformation equation tomorrow. And you will see that it will be connected to this homology mentioned earlier. Thank you very much.